My name is Alex Blanda. I work as a security engineer for Intel's Open Source Technology Center in Romania. Today I'm going to talk to you about a project that I've been working on during the last several months. It basically involves fuzzing system services in Android. I'm going to start off by giving you a brief introduction to system services, what they are, how they work, why are they an interesting target for a fuzzing campaign. Then I will move on to showing you some implementation details of a fuzzing tool that was developed for this specific purpose. And then we'll see some examples of security vulnerabilities that can be triggered using this kind of approach. Okay, so system services are a fundamental part of the Android operating system. They implement a lot of very important Android features, things like display and touch screen, network connectivity, telephony, USB, and so on. The thing is that from a security perspective, this brings us a very large attack surface. And also, given the fact that we can interact with such a large number of components, some of them may run with high system privileges, which may lead to more severe security problems. Now, these system services are implemented using a remote interface that can be written either in Java, in C, C++, these are native interfaces, or using both Java and C, C++, using the Java native interface layer. From system security perspective, the system services that are of most interest to us would be the ones that are written in C, C++, and especially from a fuzzing perspective, because generally speaking, fuzzing campaigns tend to find more issues in projects that are written in C or C++, because there is the inherent memory corruption issues. Now, to understand a little bit the opportunity that we are facing when trying to develop a fuzzing campaign for this target, we need to see a little bit some of the inside of the Android OS. So the inter-process communication mechanism that is being used in Android is the binder. Binder objects can be controlled by the Android operating system by using a reference to different objects by other system services or other services and other applications. Now, the thing that is of interest to us is the fact that some binder objects, more exactly the system services, need to be universally accessible. So they need to be universally accessible by other services and by other applications. This creates a perfect scenario for a fuzzing campaign where we could have a totally unprivileged app try to send different types of inputs to other highly privileged system services that are present in the Android operating system. Now, every Android device has a service command. You can find it in /system/bin on nearly every Android device. This command has more functionalities. The most important one is the fact that you can call a method that is implemented by a certain service and call it with certain parameters. And we will see exactly how to do this directly from the command line of an Android device. First of all, you can list the services that are available on a specific device. Now, the list is variable. Is variable based on the type of the device, the type of the version of the Android OS that is running. But basically, you need to run service list, and it will give you a full list of all the services that should be available on that certain device. As you can see, here this would be the name of the service, like an MVC, phone, SMS, media session, restrictions, and so on. And here we would have like a short description of that service. The thing that is of interest to us is the last part, which is actually the name of the remote interface that is associated with that certain service. Now, as I said, each service implements a remote interface which is written in Java or C++ that has a number of methods. We could call a method of a certain service directly from the command line by using service call. So for example, if we would have the service meminfo, we could call service call meminfo and the code for the method 13. These are the parameters that will be sent to this method. I32 means something like integer on 32 bits. I64 integer on 64 bits. S16 UTF-16 string, and so on. You can have multiple types of parameters and their actual value. For example, we have here 12 given as an integer 32 parameter. This is how we can find if a certain service is implemented in Java or in C++. You need to take into consideration that the idea of this project is to have a wholly automated tool that would take all the system services that are present on an Android device and try to fuzz all the methods. So this needs to be a completely automated process. So for each service, what we need to do is find out if that service is written in Java, if that service is written in C++. And for this, we need to have access to an Android tree. We try to find it based on the name of the remote interface. We search it by either .h or .cc++, or by its Java equivalent. And as I said, it is possible that some system services may have both Java interfaces and native ones. This is an example of a source code of an interface for a system service. Now, this is audio policy service interface. You can see the methods that are being declared: method number 1, method number 2, method number 3, and so on. Let's take, for example, the setEffect enabled method, which is method number 3. If we would like to call that method directly from the command line, we would have something like service call media audio policy, method number 3 here, and then the two parameters, which is an integer, the ID, and a boolean, which is enabled. And we can have like I3223 and I321. This is a very simple example of how this method could be called directly from the command line. And it makes it so easy to actually automate the whole process and turn it into a fuzzing tool. Now, what happens if, for example, we have a remote interface that only implements 4 methods? What happens when we try to call that service with the method number 5? We will get this type of message. So we'll get an error message like this one, not a data message. There are basically 2 cases when we can receive this type of error message. Anyway, 2 cases that are of interest to us. It is this one, when we are calling a method with a number that is larger than the total number of methods. And then there is the other one, the other case. For example, we have the iSurface composer, which is related to the surface flingers process. We have the method number 13. When we call like service call, iSurface composer and 13, we get the same error message, like not a data message. This means that Method number 13 doesn't actually point to any valid method. The number that is actually correct is the immediate one, number 14. This means that, for example, all the upcoming methods will shift +1 for their associated transaction codes. This is very important to get the transaction codes right, because each method has a number of parameters, type of parameters associated with them. And if you want to have a more intelligent fuzzing approach, you really need to have that information correct, because you want to know if you're trying to fuzz a string parameter or an integer one, and so on. So it's very important to observe this issue so you can get the transaction codes correct for each of the methods of a certain system service. There is another observation that needs to be made. When you are running from the commands from the Android shell, you do it with certain permissions. You can run it as the shell user, you can run it as a root user, you can run it as the user of a certain application that can have some permissions granted, or no permissions granted. It may happen that when we are trying to call a certain method of a certain system service, we observe that we do not have the needed permissions to actually perform that call. So in our fuzzing campaign, we need to take a step back and think, how would you like to run that tool? Would you need it to run it as a user with all permissions or a user with no permissions? Of course, if you find a bug, an issue, for example, by running the tool with absolutely no permissions, then it is clearly that the issue that you have found is a more severe issue. But however, if only for the testing scenario, you grant all the permissions and run as root, and you discover a certain issue, you can then come and minimize and discover, let's say, that you only needed a single permission for that issue to actually occur. And that's good also, because some permissions can be validly granted to a certain application. So for example, you have an app that accesses photos with a valid purpose, not with a malicious one, and also needs that permission to make that certain call that would trigger a security vulnerability. Moving on to the actual implementation of the fuzzing tool, the main idea is you have all these services that are present on an Android device, and you have a way to call the methods that are implemented by the system services directly from the command line. So the basic idea is to fuzz the methods of each system services using the service call command, using fuzzed parameters for each one of them. Now, I've used, for example, two testing scenarios, one where I run the tool with a user that has 0 permissions, and one with a user that has all the permissions. And as I've said, both scenarios are valid from a testing perspective, because in both scenarios, the issues that you can find are important or can have a significant significance. So I've tried to modularize the tool. The first module, what it tries to do is it takes the service list and it tries to store some vital information about the system services that are running on an Android device. So you take the service list and you take these pieces of information. So for each service, you take the service name, the service description, and the path to that interface, which, as I said, can be Java or C++. This would be an example for the audio policy system service. You have the name here, the description and the name of the interface. This is actually the name of the source code file, not actually the name of the system service. And the path in the tree to that specific remote interface that exposes the methods that can be called. The second module takes each system service and gathers information about the methods that it implements. So you need to parse the source file for that interface. You need to parse it and store the necessary information. You need to have the number of methods, the correct transaction codes for each of these methods. Then for each method, how many parameters does it take to call that certain method, the type of method parameters, and its path to the source file, the source code file. The third module is the actual fuzzing process. I've tried to run it using 3 modes, a dumb fuzzing mode, an intelligent fuzzing mode, and a targeted fuzzing mode. I'm going to go through each one of them and explain the differences between them. So this would be the workflow for the dumb fuzzing approach. For the data generator, so the tool is written in Python. I've used the Fuzzing Python fuzzing library, which is an open source fuzzing library, very useful. And then what you do for each service, you get like a method map where you'll have the number of methods and the transaction numbers for each of those methods. And then you proceed to fuzzing each of those functions. What you actually do is first you try to call that method with no arguments. I've actually had an issue that came up when calling a certain method with no arguments, although in its implementation it had parameters to be given. Then you try to fit it random arguments with a random number of arguments. So for example, you have a method that takes 2 parameters. You try to give it 3 or 4 parameters, a totally random type, total random values. And then you actually take into account the number of arguments, but you still keep the random values for this approach, for the dumb fuzzing approach. Now the difference between the intelligent and dumb fuzzing approach would be, first, for the intelligent approach, we take into consideration the number of parameters. So if a method has 3 parameters, we only fit it 3 parameters. And we also take into consideration the parameter type. If it receives numerical parameters, we will give it a numerical parameter, but try to fit it like abnormal values, like very large integers, very small integers, values that normally trigger issues in fuzzing campaigns. There is also the fact that we have access to the source code, so we can see some patterns. For example, many of the methods that are in an Android system service take parameters such as system permissions or user IDs or stuff like that. So we tend to have like a regular expression list, and when that list gets triggered, if we have something like a permission, we give it an actual valid Android permission and see what happens. The thing is that you need to access zones of code that otherwise would be inaccessible. So some of the parameters need to actually be valid, and that's why you can use tricks like this, like regular expression patterns and stuff like that. And you need to mix them, like have actually valid parameters and invalid parameters as well. And also type-conscious arguments and arguments that are not. So for example, you have a method that takes an integer parameter. In a scenario, you can actually give it a numerical value. In a different scenario, you can give it a string or things like that. The targeted fuzzing approach really means that you need to build mini fuzzers for each system service in particular. The priority is, as I've said earlier, the native interfaces, but Java-based interfaces are interesting as well. The thing is that regular expression patterns are not enough, so you need to actually go and look at the code and see what those methods are really expecting, and try to build a fuzzer that that feeds those certain methods parameters that are as close to valid as possible, and it would allow to access parts of code that in the dumb fuzzing scenarios and in the intelligent fuzzing scenarios wouldn't have been accessible. This is the logging process. So we execute that data. We start sending fuzz parameters to different methods for different system services. But how do you actually monitor and reproduce the issues that may come up? So in Android, you have the logging system, which is called logcat, which stores information about the systems and about the system and applications with different priorities. So you have messages with different priorities: fatal priority, error priority, information priority, and so on. What you do is you artificially insert fatal messages each time you execute a piece of data against a certain method, like this one. So here we had a test case against the createDisplay method that takes 2 parameters with the seed 0, that means no arguments, and so on, until we actually get a valid fatal message from the system, like this one, which is a segmentation fault with a certain fault address, which will be caused by the exact message above and can be reproduced using this seed. Now, there were a couple of issues with the logging process. The first one is the fact that when we are giving fuzz parameters, some of the values that we are sending are not printable. So that means that we couldn't just display them here and then try to recreate the exact string that was sent in the command line. Also, for example, you have a method that takes 4 parameters. You don't want to generate a single seed, a random seed for each of the parameters that you are sending. One idea was you could have saved the random generator state before each test case is executed and store them, but that would have been a huge waste of space because there are millions and millions of test cases that are being executed, and it wasn't feasible. So the idea is for a given test case, you generate only one seed that can be used then to reproduce the issue, and then the rest of the random seeds are a function of the initial seed and, let's say, the number of parameter. It can be like, I don't know, init seed +1, +2, something like that, anything. So this way we can solve this issue, and we can generate the fuzz parameters using a single random seed. This would be like a summary for the whole fuzzing tool with the 4 modules that I've just described to you. So just as a summary, module 1 parses the service list information and gets information about each service. You get the service ID, service description, and the interface name and path. Then the second module, for each system service, you get information about the methods that it implements. You need to know the number of methods, the type and number of the parameters, and get it right for the transaction codes. So find out which of the transaction codes actually don't point to a valid method. The third module is the module where we actually execute the fuzz data with the three fuzzing approaches, the dumb, intelligent, and targeted fuzzing approaches. And the fourth module would be the logging process that allows us to catch the issues and reproduce any type of bug that may come up. Now, I'm going to show you a little example of the type of issues that could be triggered by this type of fuzzing campaign. So the vulnerability that I'm going to talk about is present in a library in the audio policy service interface, the libaudio-policy-services.so. It has like a triple impact, let's say. First of all, it triggers denial of service situation where you need to restart all the components that are being affected. There are about 6 or 7 services that are getting killed when the issue is being triggered. If we make the attack a permanent one, you will get a denial of service that can be fixed by restarting the device, so we can actually stop the attack. And then the third and the most interesting one is the fact that it generates a media server native crash, which may or may not lead to a remote code execution situation. Now, media server is an interesting process because it runs with somewhat high system privileges, although in the latest Android version its capabilities have been limited. This is a low-cut snapshot of the services that are being killed when the issue is triggered. So as you can see here, there are about 6 or 7 services that die all at once when the issue is triggered. This is the native crash, so you get a segmentation fault in media server. This is the backtrace. As you can see, the signal and the fault address as well. And we've talked until now about how the testing scenario works. After you actually caught an issue, you need to come up with like a real valid, real life attack scenario that would make that certain bug valuable. So let's say you have an Android app that can have like no granted permissions, so totally unprivileged. It can have one granted permission or multiple permissions. It really doesn't matter because, as I said, those permissions may have a valid use. Those are being, the permissions are being used only to be able to call the certain method of a certain system service. Then you have the vulnerable service, which implements the actual vulnerable method. This can be triggered either remotely or locally. It mainly depends on the nature of the Android app that is being considered as being malicious, or or of the call that is being made to that vulnerable service. And then finally, we can have the impact, as we can, as you've seen in the previous slides for a single issue. We've had both a denial of service situation and a native crash, which could lead to a remote code execution possibility. So that would be, to sum up, the possibility of an attack scenario using the issues that you've caught using this type of fuzzing campaign. Okay, that's pretty much it. So these are my contact details. You can take a look at this GitHub page. It has a lot of interesting fuzzing projects that are related to Android. Hopefully, in the next 1 or 2 months, this fuzzing tool will also be present on that GitHub page. And thank you very much.
Thank you. Any questions? Okay, so you mentioned those vulnerabilities, and could you tell us a little bit more about the triggers?
Okay, so how can it be triggered? So I've mentioned this vulnerability here in libaudio policy service. It basically can be triggered in 2 ways. In one way that is specific to the testing scenario, which means that it can be triggered like a service call, media.audio policy, and the ID of the method, and the fuzz parameter that actually causes the crash to occur. But it also can be triggered by creating an app that has 0 permissions, so absolutely no permissions, that does the exact same call from Java layer and triggers the exact same response. So we have the 2 local denial of service situations and the media server native crash.
Thank you.
So do you see any difference when you're doing this fuzz testing on a physical device versus emulation? Is there any difference in the way things crash or any problems coming up with a proof of concept that works on different platforms?
Well, the main difference would be the fact that on a real device, the service list would be different from an emulated device. So you would have some system services that are present on an actual real device and are not present in an emulated environment. So that you wouldn't have practically access to some of the services to actually fuzz them. That would be, I think, the main difference.
Do you have any numbers on number of bugs you found, how they were distributed amongst different components of Android? So is there any statistics or on Android versions, how this changed over the versions? Any concrete numbers, graphs on that?
So I haven't done any statistics on the actual number of issues. The fact is that the project was in the beginning created for system services that are correspondent to Intel-based devices. So we try to first fix those issues. But then we are now trying to open source the project, and we've made it like try to make it run on all Android devices. The vulnerability example that I've given is can be reproduced on any Android device, so not only Intel-based. But no, I don't have any statistics.
Basic motivation of this project was for internal quality assurance of your own software.
Yeah.
So you'd recommend that anyone else doing device drivers and whatnot also include fuzzing as part of their testing environment?
Yeah, clearly. Of course, any Android device has its certain specifics. Given the nature of the hardware that the Android device runs on, you can have different drivers. And of course, it's highly recommendable that you fuzz those drivers. But for example, this is more like at a software level, and it still has an impact. Like if you have a different hardware, you will have a small number of system services that will be different from one device to another.